Welcome to video 43 in the Foundations of Computational Economics course. In this video we will be looking at the policy iterations solution method for the dynamic programming problems. And this is a practical video. We will code up this method for the inventory dynamics problem that we looked at in video 37 and in the exercise 11 as well. So policy iterations, also known as Howard policy improvement algorithm, is yet another solution method for the dynamic decision problems with the area of application to the discrete time infinite horizon problems, and being particularly well suited for the problems with finite state space. State spaces, right, or discrete states. So the main idea of the method is to break the single problem of finding the fixed point in the Bellman operator, like in value function iterations or Kalman-Rafford operators in time iterations. So to break that single problem into two steps. And then sort of going back and forth between these two steps, perform the iterations and converge to the same fixed point. So what are the two steps? Well, one is called policy valuation, and this is like solving the fixed point of the Bellman operator, but with the difference that the policy is fixed. So this is like finding the value function that corresponds to a particular fixed policy. Or in other words, you can say it's like, what's the value of using particular policy forever? Then the second step is policy improvement step, and here we are finding the optimal policy for a given value function. Okay, so the method contains all the same fundamentals, all the same components as any dynamic programming problem, and as you would imagine. And so let's look again at the general form of the Bellman equation. We have the value function, which is a function of state, on the left-hand side, and then on the right-hand side we have this maximization problem, which implements the Bellman's optimality principle, right? We are maximizing over some decisions, and by this we are finding the optimal choices, which is the policy function. And we are maximizing this expression, which contains the current period payoff, the utility function, the profit function, and the discounted expected value of being in some state in the next period, with the expectation taken with respect to all the random components in the model, conditional on the current state and current decisions. So the state process then becomes this controlled Markov process, which is controlled by different decisions. So transitions can be changed by the decisions that we're making in the current period. And the consequences of this current decisions, current choices, they are accounted for because the value that stems from this current choice changes. Okay, so like I said, in the policy iteration method, the first step is to basically drop the maximization in the right-hand side of the Bellman equation and solve this new equation, the simplified Bellman, solve it for the value function. And this is essentially finding the value of applying a particular policy, particular decisions, over and over again, forever. This is an infinite horizon problem. So in general, this is a functional equation, right? So it's a complicated thing. But if we discretize the states, or we have discrete states, then again, in general case, this is a nonlinear system of equations, essentially, right? So if the states are discretized, then these values are defined in some points, and then this is a vector and this is a vector. There is some relationship between these variables. many variables, but still we can say that this is just a system of nonlinear equations. Moreover, in many applications this becomes a linear system of equations, and you can think of situations where you have a Markov discrete choice problem with all randomness being incorporated in transition probabilities, and then then we know that this expectation is just the sum with something, namely the value function in the next state, sort of multiplied by the vector of transition probability. By the matrix of transition probabilities. So the calculation of the expectation becomes an application from linear algebra, essentially. In all other cases where this expression can be calculated as a linear function applied to the points of v of the value, then this problem becomes a linear system of equations. And then it becomes a simple thing, right? Simple thing to solve. If we can just solve the linear system in this step one of the policy iterations algorithm, then the whole algorithm starts making sense. So what about quadrature points and linear interpolation? Linear interpolation is basically taking some points in the value function, in fact, two adjacent points, and applying some weights to them. And we could write these weights into a matrix and multiply a matrix with a vector of the values, which would make it a matrix operation again. And the same thing with quadrature integration, right? We are basically taking points at some fixed grid and calculating the weighted sum. So therefore, it's not just the finite states applications where we can apply this policy evaluation step or implement the policy evaluation step in the efficient way through the linear system of equations. But every time you have to think about how to do this really, really efficiently. The second step in the policy iterations algorithm is finding a new improved policy. So this is a policy improvement step. And to do that, we are essentially just taking one evaluation of the Bellman operator, where the focus is on finding the optimal decisions that maximize the expression here, where the current approximation of the value function is inserted in the right-hand side. So this is very standard. We do this over and over again in the value function iteration, right? By sort of taking this and plugging this back in. And so policy iterations, they introduce this additional step, so which is pretty complicated. It's a functional equation in general sense. But even though there is more work to do, the policy iteration is very useful. So why is it useful? Well, it converges much faster. Unfortunately, it's in general, it's not known how much faster, but it's somewhere in between the convergence of the value function iterations and the Newton-Kantorovich, which we will look at in the next video. And that's because the step one subproblem is comparable in complexity to the value function iterations, and so you have to have a really efficient implementation, as I already said. All right. So which problems can be solved by by policy iterations? Again, all the focus is on how to efficiently implement policy evaluation. And we should think about whether it's possible to present the Bellman equation, the right-hand side of the Bellman equation, or the maximant, as a linear system. Discrete finite state space problems is where policy iterations really become much better choice than value function iterations. With other problems, as I said, it's every time you have to think, can I represent Gaussian quadrature in the matrix operations? Can I represent the three-dimensional array linear algebra like we did in the stochastic consumption savings problem? Can I represent that as a system of linear equations? Maybe a large system, but if it's still a linear system of equations, then we can unleash some efficient solvers on it. And still, gain some advantage over the value function iterations. But general algorithm is quite straightforward. We initialize a policy function or a value function, okay, but it doesn't really matter. And then do these two steps, one after another. So we compute the value of the current policy. So if we initialize the policy function, then we compute. Next step is to compute the value of this initial policy by solving the Bellman equation without the max operation for the new approximation of the value function, and then recompute the policy function by applying once the Bellman operator to the found and current approximation of the value function, and then repeat for convergence, and then go back to step 2, right? So once the policy function is updated here, then reevaluate the policy function to find the corresponding value, and then improve the policy function given the corresponding value. So we are really, instead of just taking applications of the Bellman operator, until convergence, we're doing this, back and forth between the evaluating a particular policy and then finding the value that corresponds to that, and improving the value using the found updated value function. Improving the policy using the found updated value function. Okay, so I thought that we go back to the inventory dynamics model here. Which is a finite state model, so it suits the policy iterations method quite well. Although you can write the policy iteration solver for the consumption savings problem, including the stochastic consumption savings problem, where it's just a bit more tricky to wrap your head around how to represent the Bellman equation as a linear system of equations. But let's go back to the inventory dynamics model, and we've looked at it first in video 37, I believe. Yeah, that would be 37, and exercise 11, which also has a video. So we have discrete state, discrete choice, infinite horizon problem in discrete time. The choices are these orders of new inventory. The state space is the inventory that we start the period with, and there is some stochastic demand in each period, which realizes before we make a new order. And the payoff is just the profits that we earn, right? So it's the a p parameter, which is the parameter of the profit per one sold unit of product. And then the cost of storage applied to everything that we need to store to the next period, and then a fixed cost of making an order. All right, so the sales are given by the minimum between X and D, minimum between the inventory and the demand. We have to store what we did not sell plus what we've ordered. And, you can write it like this, or you can write it like this, which is the same thing. And, of course, whether we made an order or not, that's just the indicator function for Q greater than 0. The transition rules are quite simple. So the next period stock, the next period inventory, is just given by what we have stored and what we paid for the storage. And then demand is idiosyncratic. So every time period it realizes over and over again independently from the rest of the model. Okay, the parameters is this per unit profit, the cost of ordering any amount, so fixed cost of ordering, and then the cost of storing the 1 unit of good. And we assume that D follows a truncated geometric distribution. So we have some upper bound on the problem, so the maximum demand and maximum amount that we can store. Just for simplicity, we're going to use the same upper bound for these two variables. So the problem really lives on the square, right, with integer nodes. And so D, we assume, is following a truncated geometric distribution where the probabilities of all of the variables, all of the values I from 0 up to n-1 are given by this, and then we collect the probability mass from the truncated tail in the last point. So this is what we did in exercise 11, if you remember. Now the Bellman equation is given by this expressions. The states of the problem are x and d. Choice is of course the quantity of new order, which is non-negative, and then we have the current payoff is just the profit, and then the expectation, which is quite standard. And we can expand it a little bit by saying that if we sell S, then the profit is given by SP minus X prime R, where X prime is the next period inventory, and then this indicator times the fixed cost of making an order. The expectation here is taken over the next period demand D prime, and as we just said, it is idiosyncratic, and so it makes a lot of sense to convert the problem from the value function space, like here, right? So this Bellman equation is an equation in the value function space, where the value function is a function of x and d, and we can convert it into the expected value function space, where the expected value is the function of x alone, okay? So when we solve it numerically, the expected value is going to be defined on a single grid of x's, whereas the value function will have to live on a matrix, right? For all x's and for all d's, we have to have an expected value, and then finding the fixed point is of course much simpler if you have a lower dimensional problem. All right, so that's the reason of converting the problem into the expected value space. So what is the expected value? We're going to denote it with these two letters, and this is a function of single x. This is just the expectation. This is expectation that we have in the side of the Bellman equation here, so we can substitute the expected value function right into the Bellman equation. But then, then we can take expectations on both sides of this expression of Bellman, and what we get is the expected value on the left-hand side, and then the expectation with respect to d of everything that comes here, where d enters into the quantity s and x prime. And because the problem is discrete, right? We're talking about this discrete product. Then it's natural to assume that the demand is also discrete, and that's actually already given as a truncated exponential distribution over discrete points. And so the expectation is just the sum of this integrand with the multiplied with the corresponding probability of each value of demand. Okay, and now what we have the functional equation now in the space of the expected value function. See, expected value function enters on both the right-hand side and the left-hand side. And we can work with this. The fixed point or the expected value which corresponds to or satisfies this equation is describing the solution. And then we can iterate on this right-hand side as an operator and perform value function iterations, just like we would do with Bellman equation. Now, but what is the policy function? The policy function is still the function of both x and d, right? Because the policy function is the argmax q in the original Bellman equation, which depends on both x's and d's through s and through x prime here. And as we discovered in the end of exercise 11, we actually have this property that that the optimal policy, optimal choice, doesn't seem to depend on x and d independently. And indeed, if we stare enough at this expression here, we will see that, where does q enter? The q is multiplied with r over here, and there's q that enters here, and of course q enters in the expected value through the x prime. So some of this components can be just taken out of the max and actually just forgotten in argmax. So it's like we're maximizing a function plus a constant. Constant is not important, but what's important is how q is interacting with other variables in the continuation value here. And the interaction is through this function of x and d, which, for if this function is the same, then that's what q should really depend on because that's what is important for the future. And to say the same thing in other words, let's look at the timing convention that we have in the model. So, and that's always important. Having the timing convention worked out and being very clear is an important condition for the dynamic model to be set up properly, or to be thought about properly by the researcher. There is a timing convention always embedded in the Bellman equation, just from the way it's written. Problems with the same variables but different timing conventions would have different Bellman equations. So what do we have here? We start the period with some inventory x, that's part of our state space. Then demand is realized in each time period. And that's now also part of our state space because the decision is taken after that. After demand is realized, then we take the decision as a function of both x and d, right? And the assumption that we know the current demand, the current period demand, before we make the new order is what's decided that d has to be part of the state space by definition, right? The state space is all of the variables which are important for the decisions that we model. And then the current period is computed as a function of x and d and q, because q now enters in the current payoff through the fixed cost of order and also the cost of storage. And then the next period inventory is finally known, and it's stored for the rest of the period for the given price of storage. Right, so what q really depends on is not so much on x and d individually, but on what's left after the trading period, this expression here. Because this is already known after the first two things has happened in the time period. And then given that, we sort of decide on the q. And as I said, because the future has this expression in the value function here, and that's how the q interacts with the other variables. That's what it's really conditioned on, not on x and d independently. Okay, so given that, we can then define a new kind of a variable, and let's call it the post-trade stock. This is the inventory after the trading phase. And this is given by this equivalent expressions here. This is what's left after the sales. Okay, and then we can rewrite the optimal policy function, this q function, which is the argmax. This is just a repetition. And then we can introduce y into here. So x prime becomes just y plus q, okay? And forget about the constant terms, which are independent of q, and this one, right? So the Q becomes the argmax, the optimal Q becomes the argmax of this problem here. And you can see there is no X's and D's anymore, right? The parameter in this problem is Y. And therefore, this is just a function of Y. Bearing in mind that Y has the particular interpretation with X and D. And so here we've shown that we conclude that the optimal policy function can be simplified and written not as a function of the state space X and D, but the function of this intermediate state Y, which is the going back to the timing convention, which is the point, which is the state which that is realized right here. It's like a sufficient statistic for the states X and D, just like the sufficient statistic in the endogenous grid point problem, which was the end of the period wealth. So Y is now using the same sort of ideas. Y is representing the state space sufficiently accurately so that we can condition the optimal policy just on that variable. And this is helpful because now Q is not a matrix anymore. It's just a vector. Okay, so here's the sort of resulting compact solution. So here's the solution for the inventory model. We have the fixed point problem, the Bellman equation in the expected value function terms, and then we have the definition of the policy function, which is the simplified argmax problem, right? Simplified in the sense that it's only a condition on Y. We're using the EV function that is the fixed point of the Bellman operator, and then we plug it into here and we calculate the argmax using this. So can we use these for the policy iterations? The answer is of course yes, because we can now iterate on these two notions. We can solve for the EV that is a fixed point of the Bellman operator in the simplified Bellman operator, should I say, where we can just drop the maximum, right? Compare this one with this one. This is written for a particular policy function Q of Y, where I just plug it in instead of trying to find the maximum Q over here. So this is the simplified Bellman equation where we are sticking to the policy Q of Y for the rest of the time periods. It's still a functional equation, but let's look at it in a moment. And then the second step of the policy iterations is basically improving the policy by calculating this argmax using the EV just defined in the previous step. So then we can back and forth between these two steps in the policy iteration sense. Now, the important next question is, can we simplify this problem and hopefully represent it as a linear function or linear system of equations? Let's think about that. So we have the state space, which is just the integers between 0 and some upper bound n. We have all of the variables x, d, y, and q, which live on this finite state space. And, it's just by simplifying assumption that the demand cannot be larger than n, it's going to be enough. I mean, if the demand is n, the upper bound should be chosen such that demand never goes much higher, right? Otherwise, the problem sort of doesn't make sense. You have to have a larger storage if you're facing larger demands. Okay, so let's think of EV of x as a vector, and I'm going to use EV. It's a slight misuse of notation here. EV is going to be without any brackets. This is going to be a vector with n plus 1 element. N plus 1 element corresponding to the points in S. And the now what is this EV of y plus q? Right, we need to calculate to be able to calculate this EV. Well, it's like a particular indexing of the elements of the vector v, because y plus q of y, that's going to be some quantity of stock, right? So it's an integer between 0 and n, you know, thinking or assuming that the upper bound is just going to be imposed. So these are some elements of vector EV that we take in a particular order. Now, this can be expressed as a matrix multiplication. We'll look at it in a second, but this is like permuting the elements of the vector, where the permutation matrix would allow you to do that. And once this is solved, look at this. This is just a linear function of the EV, of the elements of the vector EV. So it seems that we can express this whole equation as a linear system of equations, and then policy iterations then would work really well. So let's look at this. Imagine that the EV vector is the vector of the expected values is just given here by these numbers 11, 21, 32, 43. You can see that the first digit is basically the position of that number in the vector. And imagine that y plus q of y is giving us these indices of the EV that we need to find. So essentially the problem is how to represent, you know, indexing into EV as a matrix operation. All right, so let's just find the size of the vector and then compose this particular matrix. It has zeros everywhere except for the these elements. So we use the J vector is the indices in rows, or in each row of the matrix. And then let's look at this vector, which is just the constructed sort of indexing matrix M multiplied with the original EV. And here we are. So EV is this vector, the indices that we're interested in. The constructed matrix, you can see that it's, you know, 1 here corresponds to the 1 in the first position in the first row. 0 here corresponds to the 1 in the 0th position in the second row. 2 is corresponding to the third position in the third row, and so forth. And then once we've performed this matrix multiplication, what we have is the components of the original vector, which are now reshuffled according to this indices. Okay, so we have first, that's 21, then 0th 11, then twice the third one 32, 32, then the fourth one 0, 1, 2, 3, 4, it's 54, then the third one 43, and then so that means that we can, since we can represent this indexing problem as a matrix multiplication problem, then we can express all of our simplified Bellman equation as a linear system. So how does that happen? So again, EV is the vector of all the values of EV of x for all possible x's. So we are immediately vectorizing the problem like we always did. Now, denote this M of D, the matrix that we just constructed in the example. So this is the matrix such that it multiplied by the vector EV gives us the needed EV of y plus q of y. All right, and then just denote C of D is the matrix, the vector of representing this expression, which is the constant term with respect to EV. Now, this includes both x and d, right? But C is going to be a vector for all possible x's. Okay, then the Bellman equation can be represented by this expression, and let's compare. So it's this Bellman equation that I'm talking about, and you can see that we've denoted this whole thing as C of D, and this is going to be a matrix multiplied by EV. Okay, so this is what we have. C of D and M of D times EV. There's beta in there, and this is all inside of the weighted sum. Right, so open, do a little bit of algebra. We have this expression, which I just denoted as C bar, and we have this expression. And here, this probability of D is just a constant, so we can just pre-multiply this M of D matrix with this constant. And what we have is now the matrix M bar, which is the weighted indexing matrices, where the weighting is happening by the probabilities of various values of demand. And the whole system now, or the whole equation, can be represented by this linear system. With EVs being variables, and we can solve for EV by solving a linear system quite easily. Okay, let's now implement it. And we are starting with the code that was developed in exercise 11, in the solution to the exercise 11, with a bit of a change that I'm only looking in the infinite horizon version. And I've also combined the functions that we've written in exercise 11 as separate functions as to be methods of this class. So what's the class? The inventory model. It has all the needed parameters. Initialized, you should go back to exercise 11 to see how it was developed in video 37. Sales are given by a separate function, next period inventory. Profits are given here. The demand probabilities is what's incorporated now into the class. So this returns this truncated distribution for various points of the demand, and it can plot. So here's the correction that is needed to ensure that the probabilities sum up to 1. This is where the truncation kicks in, and we are collecting the probability mass from the tail of the geometric distribution into this last point. Okay, the Bellman equation is now also part of the class, and this is the Bellman in the expected value function space, right? And here we are going over all possible values of demand to calculate the profits. Okay, this is the extrapolation of the value function, and then here's the expression for the value function in the matrix form. Right, we're finding maximum in every column, and then the expected value is accumulated here. Now, the argmax is impossible to compute here, right, because the argmax requires this to be done for all possible values of states X and demands D, except that now we know that it can be represented more efficiently as a function of the post-trade demand. I'm sorry, post-trading stock. We have to edit now, but let's continue looking through this code, existing code. We have a VFI solver, and then we have the way to graphically represent the solution. Okay, and let's see how it works. Well, here we are, some inventory model with particular parameters. We are plotting the distribution of demand. And you can see how the probabilities decline. So the most likely value for demand is actually 0. And then there is a little blip here, very tiny, to collect the probability mass from the rest of the values of the demand. And here is the convergence of the value function iterations. And we've converged to a particular value function. The policy function is not calculated because it's harder to present in a simple graph, except now that we can do it, we should correct the code. Instead, there is the optimal policy calculator, which presents the optimal policy as a function of both d and x. And you can see that here axes are on the horizontal axis, and then d's are on the vertical. Every time that the d is larger than x, we have the same value of the policy, and it's only in the upper triangle that something happens. And because of this symmetry, we can think of the difference between x and d that really, as we showed, matters for the policy. Okay, so let's start with coding up the policy function. Let me just copy this first, and then we will implant it into the class. Okay. For the stochastic inventory dynamic model for given EV function, computes the policy function. It's a function of post trade stock. This is how we called it, right? Post trade stock as the intermediate state variable. Okay, we don't need the three-dimensional array anymore, so we need the two-dimensional array with q's in excess zeros and y equals max of x minus d0 in x is 1. So it's going to be a function of y only y, and we have to sort of bear in mind what this y is. Demand this is post trading stock. X we don't need anymore. Compute current period profits. Okay, we don't have that, right? Index the next period value. This is important. So next period value will have to enter into the maximum equation. And what's the next period value? Well, if we have y and q, we know that the x prime is just y plus q. And this is going to be a matrix now. But we have to replace the values which are too large with the upper bound. Same as before. And so now we can index EV with this I. EV is the input into this function. And by the way, let's right away replace m with self, thinking of how this will be embedded into the class. So compute the Bellman maximand. This is going to be Vm. Oh, now this P is not the profits, right? But the simplified profits or simplified payoffs, which is where? It's here. Just this that we need. So minus Q times R. Self R times Q minus self C times Q greater than 0. Now let's think about what the dimensions here are. So this is the row vector, column vector. This is the row vector. So when we say y plus q, this is going to be a matrix. So I is going to be a square matrix. Q greater than 0, that's going to be a column vector, and this is a column vector, but this is a matrix, right? EV of I, because I is a matrix. But it's fine, and this is also fine, right? Because now this greater than 0 will be performed element by element, and only for those Q's where it's greater than 0 will we have C applied. Okay, and then we can return the argmax. That's all. So let's call this optimal policy old. And this is optimal orders of new inventory for y equals max x minus d. And that's what it is now. M is not defined. Where? In VM. Okay, so I've replaced M with self everywhere. Oh, and here we go. So is this still working? Optimal policy old we want. Okay, so let's compare the old and the new. You can see that the old is ordering 7 for all of the points where x was less than d. So we are, after the trade, we're left with no inventory. And that corresponds to this first element here. So if y is 0, then we're ordering 7. And then so for, then for lower level of post-trade inventory, which would appear on this diagonal, we're ordering the 6, 5, 4, 3, 2, and then zeros after that. And that's exactly what we have here. So it's like, it's like we're looking at the diagonal of this matrix, properly aligned. Or you can also say that this is like a last column reversed. Now, first row. that we've that we use to represent the optimal policy. Okay, with this done, let's implement or embed this optimal policy calculator into the class. This is going to be here, and now we can call it from the Bellman operator. Self optimal policy of EV1. Because EV1 is now EV1 would be the updated expected value, and so the optimal policy would compute the optimal policy given that expected value. So, so this is essentially the step 2 of the policy iterator, policy iteration solver. Right? We are updating the policy using a particular expected value function. Okay, now we can resolve this and visualize all the policy all the policies, except now for the X2, instead of inventory, we have to say post-trade inventory. Because it is defined on the different in the different space. Okay, here we are. You can see that the optimal policy didn't change all that much, and that it is so 2 for 5 and 0 for 6, and that's what we had here. It's actually probably also worth plotting it as a step. As a step line instead of the plot, because everything is discrete. And we need that magic where equals mid for this to be more readable. Otherwise, what's this vertical line corresponding to 0? What does it mean? And now corresponding to 0, there is a clear 7, and to 1 it's 6, and so forth, and then we have this jump. Okay, so we have the class working. And now let's work on the policy iterations solver. Now this solver is going to be an successive approximation solver, just like the value function iterations, except that now the iteration, right, the one step is broken into two steps. So let's see, policy iter. But the function will look pretty much the same way, right? So it will have tolerance and the maximum iterations and a callback using policy iterations. And so if we are initializing the let's follow the algorithm and initialize the policy function first. Initialize policy or value function. Okay, let's initialize policy function, compute the value for the current policy. The policy is going to be denoted Q naught. And what is the initial policy? Well, if it's all zeros, that's basically we're not ordering anything, and that's fine. What will be the main loop? Okay, the main loop will have step 1, policy evaluation, and step 2, policy improvement. Well, we know what we do in the policy improvement. So here in step 1, we will calculate the EV0, which will be something, I don't know what yet. And in the policy improvement, we will calculate Q1 as the new policy. And that's going to be just the optimal policy corresponding to this EV. Maybe it shouldn't be 0. It's a self-optimal policy of EV. Okay, and so this is almost like the Bellman equation, except now we don't really need to recalculate the expected value. We just need to calculate the policy, which is the optimal policy for this given EV. And then we will calculate the error as the maximum error between Q0 and Q1. So we want to converge in policy space. And if we do, okay, we want value function EV1 and EV0. Well, these are not updated, so there will be only one EV. And when we are plotting, which one are we plotting? We're plotting EV, and this is EV1. Okay, so here EV0 is not going to exist. And I'm going to call the expected value that we compute on each iteration EV1, just to keep the plotting function the same, right? So here, this is where it's going to be important. So we want Q1 and EV1. Model self error, that's all good. So then the convergence, and this is preparing for the next step. Here we have to say Q0 equals Q1 and return EV and Q1. Well, not the EV though, right? So we need to return the policy evaluation of Q1 in the end here. So it is worth saying EV1 is going to be equal here, same as EV. Okay, so we need to write another function, which is policy valuation. and we need the policy here. The expected value of the given policy. And this calculates, does it calculate a number? No, it calculates a vector. Returns a vector EV for all points in the state space. So let's return zeros for now of self how do we say self n, right? Number of inventory levels. Yeah. So we are not done here, but we know now how to call this, and this is going to be self policy valuation of Q naught, okay, of the current Q, and this is Q is updated. This is where Q is updated, and now we can also evaluate this policy before we return Q1. Okay. So I suppose I can now start testing and calling this this solver policy iter. Solve policy iter doesn't exist. That's because I didn't run the class code. Are we still iterating? No, it was done. It was done. Okay. So probably I can show. Now, when showing, now we need the method. Input. If method equals v-phi, elif method equals policy iter. Let's raise error. Error. Known methods in solve show. Okay, and if it is policy iter, then we solve it with policy iter. Max iter tolerance callback works. Yeah. Let's leave it there like so. Method equals policy iter. Okay, well, they're all just flat, right? Because we didn't implement it yet. So what happens is that we are starting from zeros as a policy. The policy evaluation returns zeros. And for zero future, yeah, there's it doesn't make sense to make any orders, right? If there's no future. If the values of anything in the future is just zero. Okay, so that seems to be producing sensible results, although it's far from being a good test. Let's now implement the policy evaluation. So to do that, we have to go back to the formulas, right? So here's the plan for the implementation. We want to produce this matrices C bar and M bar, or better, this identity minus beta M bar, and then give it to the linear algebra solver to calculate the EVs. So let's start with that. The simpler object is C bar. Oh, and we have to do it for all possible values of demand. So we need a loop over all possible demands, and this is similar to what we did in the Bellman equation here. So let me copy this structure. Maybe copied too much. So PR is going to be a self-demand of demand PR. These are the probabilities for different levels of demand. We need to calculate the C bar for different demand level, the M bar for different demand level, and let's initialize these. Right, both of these functions are given as a weighted sum. So let's initialize them with 0 matrices. Self n, comma self n. We don't need this. And now enumerate self x for all values of the demand. Create the grid of choices. No, I guess we don't need any of this. Or maybe not yet. Grid of choices, grid of choices. What is C of D? That's for given D and for all values of X. Okay, so we probably still need a grid of axes. Well, that's self x. That already exists. So mean of xd times p minus y plus y q of y of r. Oh, so we need to implement this, which is a new thing. Let's see. Next, x and profits. Can we calculate this as profits? Because that's what they are, isn't it right? This is what doesn't depend on EV. So these are all just the profits of the calculated for a particular x, d, y. Y is new. So x, d, and q. X, D, and Q. Right. Now we need to have a vector there, and so profits, and here's the line that we need. For all x's and for given D in the loop. And where does Q come from? Well, Q is given here, and it should be Q corresponding to the values of Y. So in here we have to compute the Y's as X minus sales X. Right. Policy evaluation here. So Y is X minus self sales of X and D, where by X I mean all X's, so the whole grid of X. So what's going to happen here? Sales xd, sales is going to take us the minimum between x and d, and that's going to be subtracted from x. So this is essentially the same as this, right? Yeah, we've seen that in the beginning somewhere. Yeah, there. And I need to give it a particular Q. So let's say this is post-trade stock. The post-trade stock cannot be larger than the upper bound, right? Because that's x minus something, and x is within the bound. So that means that these are just simply numbers between 0 and capital M. So can I just say this now? So this will be Q's corresponding to these numbers y, and this is the optimal orders corresponding to all possible x's for the given d. And that's exactly what I need, right? So this is for a given d for all possible x's. These are the optimal policy, or the policy which is given to the policy evaluation. This is the policy to be evaluated. So okay, this should be right. So these are the profits. These are the profits, and let's think about what we need this for. This is essentially all we need to have for the C of D, right, to calculate the C bar. And so, and that means that the C bar can be incremented with PR of J times P. All right. Okay, this should work. Let's say here for clarity that Y is post-trade stock for all values of X and current D. Profits for all values of X. Conditional on D and Y now. And Q of Y and Q. And so C bar can be updated, right? And when this loop completes, then the C bar will be calculated completely, because this is just a weighted sum. Okay, what about the M bar? We want to be able to say M bar is PR of J times something. So what is that something? Well, M bar is this M of D, and M of D is the matrix that computes the EV of this guy, the matrix, right? And here's our exercise. So let me copy this here. Here's an exercise. EV was given with that. J is the representation of Y. Let's actually keep it like this. This is going to be Y plus the Q of Y. And again, this can be over capital N, over the upper bound. So as in the optimal policy, we have to cap it, right, with self upper. But this is not Q, this is Q of Y, right? And this is what? this is next period stock for all x, conditional on D and Q. That's what it is. And now we can create this M matrix, the matrix of reindexing, the transformation matrix. So this is going to be zeros with self n, the square matrix, integer, transformation matrix, range n and j. Again, self n, j equals 1. Good. This is the transformation. So this is the matrix that would be multiplied with EV. And so we can say M bar is can now be updated to this. Okay. So I don't think we need any of this anymore. Because now we've completed all of the operations inside of this loop. And so when loop completes, then we have the C bar and M bar matrices. And now then we have to calculate the matrix, this one, which is the identity minus beta M bar. So let me call it A, and it's going to be equal NP, I? Do I remember this correctly? Yep. And n, number of rows in the output, number of columns in the output, if none defaults to n. Okay, so this is going to be ni of self n minus self beta times, beta is given, times m bar. Okay, and then finally, EV is just the linear lean-alk solve. Lean-alk solve, NumPy. It needs A and B, essentially. Okay, so A, and on the other side, it's just the C bar. And we can return EV. Okay, let's test this. Bugs. Arrays used to is indices must be of integer Boolean type. So this is here, self n. So j is not of integer type. Let's see why. Arrays used of integers. So j must be of integer type. Y self x minus self sales x and d. I mean, I could just say that j should be int. Or we can change it everywhere and say that this is a range d type int. Let's make this change. It didn't help, but we've changed something, and let's check that the previous solver works. And it does. And here again, arrays used as indices must be of integer Boolean type. It's the transformation matrix that is not working. Let's try to investigate. So they are fine numbers, integer numbers, but are they floats? It is float 64. So how does J's type determined? Oh, wait a second. J is used for enumeration. Double use of a variable. That's not good at all. That was a terrible bug. It's the PR of J that we're using here. And I is going to be the next period stock. And it's with I that we have a problem, right? Yeah. So it's minimum of upper. What's upper? Max inventory. Max inventory is 10. So I guess Q must be a float. And how do we do? Where does Q come from? Comes from zeros. Let's say D type here is int. And there we are. Okay, so we're printing a whole bunch of things now. It is here. Ooh, interesting. Did we converge? Seems so, but clearly the results that we get are very different from what we had from value function iteration. Look at this. This is the value function iteration solution, and this is solution from the policy iteration. How do they even compare? Interesting. Value function sort of fluctuates. That's an interesting bug. So it seems that the maximum is not taken somewhere, right? It says that, you know, having too much stock is actually not good. It's not even. It's even worse than having nothing, right? So you're paying too much for storage. But here it sort of fluctuates, which is very interesting. And also, why is there more red lines here than needed? There must be a problem with the shape. So if I print Q1 here, together with its shape, shape is not defined. How is Q1 26 by 26? It should be just a vector. Okay, so there's clearly a problem. Why is this a vector? So it starts as a vector, then EV should be a vector as well, and this should be a vector. let me turn this other print off, actually. So let's see first what EV does. Oh, too much output. And we don't need to resolve the VFI. So EV is 26 by 26. And so that is already a problem, right? Because the expected values should be just defined as a function of one variable x. So it should only have, it should be just a vector. So it must be that C bar is a matrix. Why is C bar a matrix? Well, that's only possible if P is a matrix. Oh, it's a matrix because I accidentally defined it as a matrix. C bar is just a vector. It's the M bar which is the matrix. How about now? Okay, dimensions are right, and the graphs look okay. Okay, let's kill the prints. And let's actually already compare. So value function iterations. Here from 7 all the way down to 5. And here the policy is from 7 all the way down to, well, 5. 2 for 5 and then nothing. 2 for 5 and then nothing. And the policy, I'm sorry, and the value is between 550 and a little bit lower than 50 on this end. Look at that. Now, how many iterations it took for the value function to converge? It seems that it only took 3. Whereas it took, many for the, for the policy iteration. For policy iteration, it took 3 iterations to converge. Or something like that. And we got exactly same policy. The letter coming down and then jumping down to 0. And this exactly same value. Isn't that amazing? Okay, well, let's first make sure that we get the same answer, actually. So E1Q1, EV2Q2. And I also want to calculate the iterations. So in the callback function, let's just print iteration number. And the iteration is given, right? Yeah. Iter. Without the line break. Okay, and here let's print difference in value functions. In policy functions. What's the EV1 minus EV2? Q1 minus Q2. Okay, and let's run again. Something's wrong. Only side 1 arrays can be converted to Python scalars. Yeah. NP max, A max. Let's look at the maximum difference. So in the value functions, we get a little bit of difference, but nothing in the policy function. Well, of course, these are just integers, and here we have floats. What about the let's actually say 3e to get the magnitude. What about the number of iterations? So here we've got 149 iterations. Here we have 4. You can see the difference in convergence speeds here. And the difference in the value function is 10 to the minus 6. What's the tolerance of the convergence? Well, that's 10 to the minus 6 tolerance, right? So the difference in value function is corresponding to the tolerance of the successive approximation solver. This is what we would expect, right? The solver stops at that tolerance, and then of course you cannot expect the answers to be even closer from 2 different methods. But so here we are. The policy iterations, as you can see, they're much faster. That's what we've seen. And you can yourself run the model for different parameter values and see whether you can find the way where at least the difference is not as drastic. But more work is needed on each iteration in the policy iterations, right? Because we need to solve this additional functional equation. Well, we have succeeded in representing it as a linear function or a linear equation solver, so it doesn't take any time. But even if we didn't, in a problem like this, it seems that running 100 or more iterations might actually be slower than running just a few, even though they're more work. And that's the main conclusion for the policy iterations. It's worth mentioning that sometimes something called a modified policy iteration algorithm is used, and this is essentially an idea of running running a finite forward simulation of the Bellman operator instead of solving for the policy, instead of solving the simplified Bellman equation to evaluate a policy. Why would you do that? Well, that's essentially in the situations where you cannot efficiently solve the simplified Bellman as a system of linear equations. Then you might want to apply Bellman operator with fixed policy several times to update the values and take it as that for the first step. But then the conversion speed is not optimal, right? Because now you're not taking, you're not updating in the best possible way. And so it is possible as an approach to do this finite forward simulation, or taking a finite number of Bellman operator evaluations, but the efficiency of the policy iteration is not going to be as good. Okay, there are some further learning resources. There's a link here that should actually work to the material on discrete state dynamic programming in general in CompEcon. And that's it for policy iterations. See you in the next video.